Hello, my name is Hauke Herrnring, and I'm happy to present the simulation of two-dimensional ice crushing processes with the Mohr-Coulomb Nodal Split model. Why are ice loads relevant for the design of marine structures? Actually, there are a lot of activities in the polar regions. There are, on one hand, commercial activities, which are, for example, commercial shipping, oil and gas industry or tourism, but also you see scientific ship operations or also naval ship operations in polar regions. What are the consequences? Some examples are shown on the slide. Here is given a collapsed lighthouse, or the consequence, the damage of a collision of an ice-strengthened vessel with a small iceberg. I would like to start with a brief introduction into ice structure interaction. Fundamentally, or basically, you could subdivide your process into two classes. On one hand, into failure away from the interface or the contact interface, and in the direct domain of the contact interface. These are both processes, spalling and crushing. Other processes are, for example, bending failure or radial cracking or buckling failure, or also creeping. But these are very important because when you think about the maximum structural ice loads, these processes on the interface itself are finally limiting the forces on the structure, and so I think in our perspective these are especially important to understand these processes very well and also represent these processes in a very accurate form. Basically, you have to subdivide it into these processes or the ice loads into ductile loads and brittle loads at small velocities. Here, as shown at 0.1 millimeters per second, ice behaves ductile. You see no force oscillations, and the process is mainly limited by continuous continuum mechanics and continuous disintegration. On the other hand, you see brittle loads. In case of brittle loads, you have drastic force oscillations and some localizations effects, which are called high pressure zones. I illustrated these high pressure zones here. You see these high pressure zones are created due to spalling, because you see fracture going out of the interaction to the outer surface, and some disintegration behavior here in the interface itself, which are also here shown or nicely illustrated in a photo of a real ice structure interaction experiment, where you see spalling and also the crushed layer here in the center of the specimen. This means that ice structure interaction is always also in brittle mode limited by spalling, so fracture mechanics, and also the continuous mechanics problem, dynamic mechanics problem here in the crushed layer. And those processes are very important for the ice loads. So our approach to represent these processes is the Mohr-Coulomb Nodal Split model. The purpose of this model is, or the objective of this model is to represent forces and contact pressure in an efficient way. Because this model is intended as a design load model, forces and pressures are, in our perspective, very important for the structural feedback. We are considering spalling and crushing to represent high pressure zones, and the material behavior of ice is equalized. So as we are focusing on brittle loads, the creeping is neglected, and to create an effective material use, cracks are represented in a smeared form, and for example, micro-cracking or complex mechanisms like sintering or healing of the material are not represented. The fundamental material behavior is described by the Mohr-Coulomb material model, which is known also for rock mechanics or soil mechanics. And yeah, we characterize the material according to a common database, which was developed by my colleague Björn Kellner. And I use the relevant data, and you see that I achieve a quite nice or good representation of the general trend. The Mohr-Coulomb Nodal Split model was implemented in LS-Oyna release 11.1. I use the ME105-Simulation, which is a very, the common Mohr-Coulomb material model together with the constraint tight node failure, which is the node splitting function in LS-Oyna. Node splitting is very important. We use node splitting because for compressive failure, you have to, or for physical modeling of compressive failure, you have to be careful with element erosion, because if you use element erosion to represent failure, this means that you are delete elements which actually will transmit load also in case of failure. And so I think the element type or the node splitting approach is much more will represent the physical behavior of ice more accurate, and we are using this is the reason because we are using this approach. During node splitting, in case of failure, only the nodes are detached from the neighbor elements and the mass and volume is preserved. Actually, we also use element erosion, but we use it as for specific physical-based phenomena as pulverization and pressure melting, and to simulate or consider also the context between broken elements. We use single surface context, which is fully surface-based contact with self-friction and a friction coefficient of 0.05. Here are some first validation for an uniaxial tension and compression test, and we achieve in compression failure stress of 5.2 megapascal and in tension for 1.73. Now our considered or studied model, we use consider a level ice condition where you push an ice sheet against the test structure. In our simulation, we did it the other way around. We push the structure into the ice is fixed on the right side, and we move this test structure, blue test structure, with a velocity of 0.1 meter per second. The coupling was implemented by a simple contact node to surface contact. The dimension of the ice feature is 5 meters long and 1 meter thick. We implemented also hydrostatic forces. For that, we used segment-based approach, where we add to all segments, also the internal faces, a pressure which was computed according to the simple equation. That means that we have a pressure independence of the y-coordinate for the submerged element, or otherwise if the element is beyond the water through the free surface, we set the pressure equals 0. We did some validation with a single element or complex structures, and we achieved for all models the same results, which means that the algorithm is working. Now I would like to show the results of the simulations. First, for the simulation without hydrostatic and gravity, you see the fragments just flew out of the contact interface, and at the end, because of the absence of restoring forces, a large fragment will detached and pushed out of the will leave the interface. or the interaction domain. It's different for the floating scenario here. For the submerged and also for the non-submerged parts, the elements stay in the interface and or pushed back, and you see this nice rubble generation in on top and also in the submerged part. So also some comparison of the pressures for both simulations. In orange you see the floating scenario, and in blue the floating scenarios, and orange the non-floating without hydrostatic. And in the first stage for the ideal flat first impact for the ideal flat scenario, there are no differences for both simulation. We achieve pressures up to 100% of the compressive strength of the Mohr-Coulomb model. And after that, you have an intermediate phase where no loads are transmitted due to the huge broken fragment. And after that, there starts this continuous crushing process. So in this case, the hydrostatic solution, or the with hydrostatic floating solution, there you see that it's slightly higher forces. If you compare the simulation results to field observations and also laboratory experience, you see a good agreement and the general behavior. So there's some rubble generation also on top of the ice surface, and also the different stages. So for the ideal first contact and the subsequent crushing process. So I would like to conclude my talk. So the used Mohr-Coulomb Nodal Split model was able to simulate the crushing process. The model was successfully extended by hydrostatic effects. Hydrostatic effects increase the maximum ice loads only to a small extent, but they are very important to simulate realistic scenarios, so this rubble generation and so on. We have to distinguish between the ideal flat first contact and the subsequent crushing phase, where we have also these high pressure zones, but both phases are very different, and I think in future designs or dimensioning the process, we have to be careful which scenario is the most critical for our structure. So I would like to say thank you and hope for future discussion. Thank you.